Today I'm going to be talking about using BGC floats in taxonomy to observe the impact of marine heat waves in the microbial ecosystem. And I am focused in the Northeast Pacific Ocean, where two very big marine heat waves happened, one between 2013 and 16, the other one between the end of 2018 to 2020. And we happened to have BGC float data there for over a decade. So we can really see how particle fluxes changed before, during, and after marine heat waves. So marine heat waves happen everywhere in the globe. They can be more resistant or less resistant. Some of them last a few months, some of them last a few years. The first marine heat wave in the Northeast Pacific over here was called the blob event, and it lasted for over 2 years. So 2 winters were really impacted by these heat waves. So the formation of these 2 marine heat waves was different. So the first marine heat wave was caused by an atmospheric ridge that formed in North America and prevented the ocean from cooling in 2013 to 2014. And because of this prevention of cooling, there was not a lot of vertical mixing, not a lot of nutrients was being renewed at the surface, and then in the following summer, then the phytoplankton started suffering because this area really relies on vertical inputs of nutrients, such as nitrate, phosphate, and iron especially. So that region in the first marine heat wave was super deprived in iron in the second year. But for the second marine heat wave, it was not like that. So here is a time series showing temperature, salinity, and density. And this is the first marine heat wave. This is the second marine heat wave. You see very warm waters, but in the second marine heat wave, you see a lot of freshness. So the water was basically lighter than previous years, and this also prevented ocean nutrient renewal. So I was interested in the area, and because we had floats with backscatter data, which is a proxy for POC, and we also have a very consistent time series program. It's a cruise that goes every season through Canada, so it's a Canadian campaign, and they sample a lot of parameters, including biological parameters. I was interested in pairing the biology with POC to understand how changes in microbial communities during these marine heat waves affected particle production and export. So there is already known that the first marine heat wave had a big change in phytoplankton composition, but they didn't know about protozooplankton, zooplankton, which are also drivers of POC fluxes. And little is known about the second marine heat wave. So I paired genetics data for over a decade. This genetics data was not even collected for this. It was collected for bacteria. So I talked to people and we recycled the samples. We did a lot of samples. So this is taking a very long time because it's a side project for a lot of people. But we reanalyzed all of the genetics data to pair with this POC. And you'll see that POC production was very anomalous during these marine heat waves, and we wanted to know why, who were producing this POC, and what was happening with the POC. So I paired BGC floats. We have time series before, during, and after marine heat waves between 2011 and 2022. 3 floats. The third float was there for many years, so it was a very nice data set. I also use BGC floats as a platform for physical changes to take a look at temperature and salinity variability. We also monitor nutrient changes to estimate net community production and see what was the potential of the organic carbon production to be exported during these marine heat waves, and this was done with nitrate data. EBeam helped me very much. I'm not showing BXCP now because it's too much stuff. I'm going to focus on POC and genetics today. But there is also NCP. I used biooptics, so I used chlorophyll from fluorescence to match up with phytoplankton activity and backscatter to estimate POC. As you already heard, chlorophyll to fluorescence is not really chlorophyll. So we did a very nice correction using satellite data and bottle data. And this was done by Jackie Long. So we could have really reliable chlorophyll data to match up with our carbon. And then I use HPLC data for phytoplankton composition at surface. So this data was collected between 2013, 2021, but it's only for the surface of the ocean, and also just gives me an idea of groups of phytoplankton, and not very specific orders or genus. And this is when genetics comes. So we have genetics for phytoplankton for the upper 150 meters, zooplankton, protozooplankton for the upper 300 meters, because you're going to see that POC really changed in the mesopelagic, and we were interested in understanding if there was a role of zooplankton grazing and respiring in the mesopelagic. So, yeah. So, backscatter data is not quality controlled right now, and you need to do your own quality control. So this is how a time series of 10 years in the Northeast Pacific Ocean looks like. You see that it's super polluted. Oh, the background. Okay, it's this one. So there I use a methodology from GRID to clean up data, a little bit of modification from another paper from before, it doesn't matter, but a little modification, and then you can see this clean data where the blue is really where there is no particles. Another nice thing about these methodologies is that you can separate signals in the backscatter profile and separate big particles from small particles down to 100 micrometers. So the very large particles can be separated, so we can take a look at like fluxes and how they change over time. And so this is small particles versus large particles. So you can see in the time series that small particles were really anomalous during those two marine heat waves, especially in the mesopelagic, in the upper 300 meters, and a lot of particle production in the second marine heat wave that you can see above the mixed layer, but not really a big change in that first marine heat wave. When we take a look at large particles, we don't really see a difference. So I just isolated small particles and I took a look at the small particles and how they change over time. And then looking at these big blobs of backscatter or POC, we can then expand it over the year just to take a look at how POC was produced and propagated on those years. So zooming in these marine heat wave years, first marine heat wave, the biggest impact was in 2015. And you can see that the particle production and export was mainly during springtime. You also have export throughout the year until late summer when the second bloom comes up. But then in 2019 is when you can really see that this spring bloom drove a very high export. And then this export kind of persists and slowly dies out throughout the year. So then we can take a look at POC anomalies just to see if this propagation was normal in other years, the years that we don't have the marine heat waves, or if it was a feature from the marine heat waves. So you can see the green is positive anomalies. You have a lot of POC in relation to non-marine heat waves, and then purple will have negative anomalies. You can really see that although the first marine heat wave started in 2014, it was only in 2015 that there is this very big anomalous feature. In 2019, lots of production and lots of export and this accumulation and slow kind of remineralization. You see these two accumulations over here, this one from the spring, this one from the summer. And then we wanted to understand who were the producers. Did we have a different microbial community growing? Did we have different zooplankton growing that could be grazing faster or slower, and where were they in the water column? So, starting with phytoplankton, HPLC data down to phylum, surface samples only, we can see that in the first marine heat wave, chlorophytes grew way more than in other years. And then in that second marine heat wave, during the summertime, a lot of diatoms grew. But you don't really see anything super different other than that. Then when we go to genetics is when you can go down to orders and genus. And the most striking difference between a marine heatwave year and a non-marine heatwave year. So red is a marine blob year, marine heatwave year, and blue a non-marine heatwave year, is that Phaeocystis grew way more during the marine heatwave, and they are super small. They produce a lot of sulfur components, and this is tied with protozooplankton that we saw growing. Other groups that grew more during marine heatwaves are silicoflagellates and chlorophytes, corroborating with the HPLC data. And then other groups decreased. So copolithophorids decreased a lot, and they are usually the fast sinkers. Also, other groups of chlorophytes decreased, and some other smaller groups decreased. When we go to protozooplankton, one group increased. It actually showed up during the first marine heat wave. It was never seen before, and they were the regularians. And they are known to produce strontium sulfate skeletons, and I think they are related to the phytoplankton over here, Phaeocystis. And they grew a lot. The x-axis is different for all of them, but this one is the dominating species. And then when you go down to, or up to, microzooplankton, we could see that during the marine heat waves, a lot of grazers grew, but also a lot of scavengers grew in the mesopelagic. So where that the POC was staying between 100 meters and 300 meters, we saw that a lot of grazers showed up. When we look at the second marine heat wave, I don't have the phytoplankton data yet because this is not ready yet, but I have zooplankton and protozooplankton data to show. Acantharia was also found during the second marine heat wave, that protozooplankton that produces strontium skeletons, but also a lot of chordata groups like doliolids and larvaceans and siphonophores grew in that second marine heat wave. So you see that large POC being produced in that second marine heat wave, a lot being exported and accumulating. So we think that these guys, they're super filter feeders. They should be facilitating the transport of POC down to the mesopelagic ocean. Also, the copepods were dominated less our genetic samples in 2019, but we have a presence of a new copepod that was a little bigger, but you could tell that so much POC, probably a lot of food for larger copepods. So just the question, how changes in microbial communities during marine heat waves affected particle production and export? Just tying the POC with the biology. High POC production, especially during spring blooms, and especially during that second marine heat wave, had also high export potential. Don't show NCP here, a little bit more than that. Phytoplankton changed composition, as we saw, Phaeocystis and Chlorophysis grew way more than in non-marine heat wave years. They're super tiny, they sink slower. Radiolarians appeared for the first time in the area, and we think they are associated with Phaeocystis because of sulfur. Herbivores dominated surface, the copepods. Scavengers dominated the subsurface. You see them showing up in the mesopelagic and probably recycling that POC that was accumulating there. Doliolids and siphonophores dominated the second marine heat wave. It was the first time that they showed up in this area, and I heard that they persisted until this day. They're efficient filter feeders and migrators, so probably they are facilitating this export over here. But why mesopelagic accumulation? Why do we see this amount of POC accumulating and being super slowly remineralized? You don't see like super fast export going on. We think that high temperatures probably increased high phytoplankton mortality, so they could have been growing and sinking and growing and sinking. Also, there was iron limitation during the first marine heat wave, so maybe phytoplankton became nutrient stressed and also died. Lots of grazers removed surface POC constantly and fast. We could see at the second case, the very big zooplankton grazing. Smaller particles are slowly scavenged and respired. So when you have a lot of small particles sinking, they sink way slower, and probably were getting slower and slower and slower as the scavengers were recycling this organic matter. So it was getting a little bit harder for them to sink. So they probably became way more close to a dissolved matter than a particulate matter. So these will decrease the prospects for fast particles sinking below the mesoplast. So this is not done yet. I'm still waiting for the phytoplankton data from the genetics, especially for that big diatom signal that appears on the HPLC for the second marine heat wave, so we can see which were the groups growing. And then that's it. Any questions?
Because you do have bacterial genetics, is there a reason you didn't include it in the map?
It's already published. That's how I found out.
Yeah.
So I did an interview for an article about the paper that I published in 2019 about the first marine heat wave, and the person that was doing the genetics for the first marine heat wave was in this article. And then I told her, hey, I have this POC. Do you want to do something? And she told me, oh, I have all these leftovers. Let's reanalyze them. So there is it's already published in Science, I think, or Nature. And all of the bacteria are different, completely different. So
I see that you mentioned about like QC in your data to look at the backscattering coefficients, correct? So what specific procedures did you use? I assume that you focused on the adjusted values and also did selected QC sites of 1 and 2, and also used either the adjuster or the delay mode. Did you take any other steps apart from these quality steps before analyzing the data?
yes, so the corrected data on the S-cross is not corrected for BDP, so you need to do it yourself. And Nathan Briggs 2020 that I showed here has a very nice paper on the correction, and then his supplementary material has a lot of step-by-step process that you can do. But basically, you really need to remove the background that has, sensor noise, background signal that does not belong to that POC that is falling, that has a little bit to do with like older water masses, and almost like a DOM to POM stuff. So you remove that, and in his paper it shows this step by step, and then you can separate the big particles and the small particles. But it's a little step-by-step process. It's not difficult.
And I assume that was only for backscattering, and that correction is not quite applicable to the other geochemical or physical variables.
No, this is a backscatter. It's a backscatter stuff. And honestly, the correction is very small. Some floats, they have higher noises than others. So when you're working multiple floats and combining multiple floats, it's important to do this QC to remove this background. But the background is like 1 order of magnitude lower than the concentration, the BDP signal itself. So it's not like crazy.
Good talk. It's nice to have 2 marine heat waves comparison.
Yeah.
One is a part. Marine heat waves primarily, is the upper ocean phenomenon. So 100, 150 meters. And then that warming signal actually propagates from west to east, very rapidly. So by the end of 2015, they already hit California. So, but your BGC Argo pretty much stayed near the station top. How you consolidate a surface moving signal versus your stationary, semi-stationary BGC Argo signal?
Well, I assume it's semi-Lagrangian, and that's it. And for the genetics, we actually, it moves a little bit. For the genetics, the line P comes and crosses this area here. And so we use the data collected from stations that are closest to the floats, so we can better match. I mean, I can do the best that I can with what I have, right?
If you do a daily profile.
But then I would need a physical oceanographer to help me. I'm not even a physical oceanographer. I have too much stuff going on already. Maybe we'll do it. Maybe we convince Ken.
If we did a daily proposal, the floats would have all run out of battery power and wouldn't have.
And you wouldn't have these 10 years of data. You have 3 years of data. So.
All right, as the peacemaker, what you can do is you can ask NSF for your own floats, right? You can actually, it's something that's important to mention is like, we're building a global array, but that NSF is fully interested in funding floats and other things to be part of process studies. So,
Maybe we write a proposal and then we show them that it's important.
But this is an ongoing discussion between the community and BGC Argo, because there are different conflicting, interests, right? And then but our goal, GO-BGC and BGC Argo, is to create a sustained global array. And in order to meet those goals, we cannot profile faster. We cannot do it in one day unless someone has $100 million per year to fund this. That's just the bottom line, right? And then so we have but the science that it enables by looking at statistical, aggregation of, look into diurnal cycles of oxygen, diurnal cycles of temperature, look at impacts of storms. So we won't be able to look at what this one specific typhoon did, right? But we will be able to say in a statistical sense, what is the impact of all tropical cyclones on productivity in the North Pacific? Well, that's the goal, right? And then maybe we can use mapping techniques and artificial intelligence to try to, establish what did this one particular cyclone did. And this is kind of what like the meteorological community is doing, right? What was the probability that this specific, hurricane, why was it this strong? Because of climate change. And they're able to now start assigning probabilities to those. So that's maybe where ocean science can go as well. But that is, that is a fascinating scientific, and I hope that these answers will be, discovered in the next decade or so.